Hello. All right. Okay. Give a moment for setup and arrival. Just move this a little bit over. No, wrong way. Oh, okay. Yeah. But give about 5 minutes for prep. Yep. The camera's looking wonky, but that's fine. You know what? I keep doing that. I need to go like this. Haha. You know what? I was right the first time. Alrighty. Okay, there we go. That suits me just fine. So, salutations and welcome. Thank you for being here today. I'm going to pick up where I left off. But before I do, as we are picking up with multiplication and the distributive property of multiplication over addition, I would like to go over a couple things that came up last video. The thing about a Googleplex, which I lovingly also have here in Wikipedia to help make sure I am right generally. So a Googleplex basically is the number 10 to the 10th power to the 100th power. This essentially means 1 with a lot of zeros behind it. Historically, in 1920, Edward Kastner's 9-year-old nephew, Milton Sirota, coined the term Googol, spelled Googol, which is 10 to the 100th power, and then proposed in further terms Googleplex to be 1 followed by writing zeros until you get tired. Kastner decided to adopt a more formal definition because different people get tired at different times. So therefore it became 10 to the 10 to the 100th. It's a lot of zeros, essentially. Googleplex just means a lot of zeros. A number into which things go on and on and on and on. So the 10 to the 10 to the 100th is shorthand for a Googleplex written out. So it's a very specific number, the Googleplex number. Also, a Googleplex is the headquarters for Google. Trying to look it up on just willy-nilly on the internet yields some varied results. Also, I'd like to highlight the reference towards Tom Laurier. Yep. If I can pronounce it, I'll be doing everyone a favor. But he posted, a musician, an artist who wrote the song New Math. I highly recommend it. The link is in the description below, as is the link to Alan Becker's Animation versus Math. That is something I linked in the previous video. I highly recommend you go see it. It's very fun. And then there is a second link under Alan Becker's Animation versus Math, which explains frame for frame what the original is about, because it's very dense in math lingo and pieces and lots to see there. Alrighty. Yeah, give a. Oh, we still have another minute. Oh. So, with the recapped, I am gonna go over some stuff. Just gonna begin. So where we left off is the distributive property of multiplication and addition. So what that is, in letters, because we always start with letters, it seems like, is if you have A times B plus C, I think we just barely got over this. That is the same as A times B plus A times C. So an example thereof is 5 times 4 plus 3. I think this is the example I had last time. So if we were to do this bit first, in parentheses we have 4 plus 3, which is 7, times 5. 5 times 7 is 35. But with this distributive property, we have 5 times 4 plus 5 times 3. 5 times 4 is 20, plus 5 times 3 is 15. 20 plus 15 is 35, which is the same. And we will get over as to why this is done first in this setting, and these multiplication pieces are done first before this addition. Okay, so there's a note I would like to make about solving applications. So when something is an application, so like applied mathematics, it gets a little more word problem-y. So solving applications, they will involve something called a denominative. Excuse me. Nope, not a denominative, a denominative. Nope. Sorry. Denominate. A denominate number. I'll get there eventually. I circled the drain when it comes to finding the right word. So a denominate number simply means a described number. So if you have the number 19, you can describe it by saying $19 or 19 feet or 19 people. But this is what is describing the 19. Honestly, numbers are just adjectives outside of mathematics. 19 what? What does 19 mean in this context? So it's very important to know in the context which numbers are being used, such as money, area, population, and so forth. So when operating with denominate numbers, let's say we have 4 people increased by 2 people. And because we know that increase by means add, we know that 4 plus 2, we are adding the 4 and the 2. But specifically, this is important because they are both the same thing. If we were to add 4 people plus $2, that answer does not really yield anything useful. So it has to be of the same denominate number. It's 4 and 2 is 6 people. Always, 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 always label your answers, because sometimes that's what is the most important. It doesn't really matter this number as long as it's describing the thing. So we had 6. So what does 6 mean all by itself? Not really anything until you put the people. Or if we have 5 times 6 feet, that would be 5 and 6, which would be 30 feet. And what that would look like is we have 6 feet. Mine, this is not drawn to scale. And we'd have 5 of those. Assuming these are all equal, then that would be 30 feet. Alrighty. So a following example of further multiplication would be a tire is $47 per tire, where the dollar per tire is denominative. So they are $47 a tire. A car has 4 tires. If you were to replace all of them, that is to get 4 tires all at the same time at this price, it'd be 47 times 4. So 4 times 4 is 16. This is in the tens place, so you place the 0. And then 7 times 4 is 28. 1, 6 plus 2 is 8. And 8. So that'd be $188 for 4 tires. That is for 1 tire. Then for 4 tires, that would be $188, which would be a very nice price indeed, to be honest. Or they'd be really, really bad tires. Okay. So further into another example, multiplication, something very much like addition, we go with carrying over. So we have 56 times 47 as an example. So we start with this bottom number, and you can either, depending on how you feel comfortable doing the math, start with the 4 or the 7. If you start with the 4, you need to start your number off with a 0 because the 4 is in the tens place and there is nothing in the ones place. So 4 and 5 also being in the tens place, you put another 0. So 4 and 5 is 20. Drop a 0, 4 and 6. Sorry, I just lost my mind. 4 and 6 is 24. So you have used up all that 4. And now you do the 7. 7's in the ones place. 7 and 5. Yep, sorry. 7 and 5 is 35. And that's also in the tens place. And then 7 and 6, which is 42, if I am not mistaken. So then you sum down. So we have 2 in the ones, 4 and 4 is 8. And 5 is 13. Carried that 1. So 1, 2, 3, 4, 5, 6. And then the 2. And that is going both, that is going left to right. Now, going right to left. Because that has a lot of numbers to sum. If this is where your strength is, try to do from left or right in the multiplication stage, so that all you'd have to do is a lot of simple sums as opposed to complicated multiplication. Because we know 5 and 4, 4 and 6, very simple things, and they go out to be in your sums. So it's very simple in that respect. Now, from right to left, we have 7 and 6. It's 7 times 6 is 42. And the carry can work in this case. So you bring the 4 over here instead of bringing it down. So 7 and 5 is 35, 36, 37, 38, 39. Because we added the carry after we multiplied the 5. And that's all we did with the 7. That was everything to do with the 7 already done. So we've used up the 7, we're going to the 4. 4 times 6 is 24. We carry the 2, we've used that 4, so we just put 2 over it. 4 times 5 is 20, 21, 22. And because there's nothing to carry over that 2, that is what we have. And at this point, we sum And you can sum from either left to right or right to left. Again, it has to do with however comfortable you are. 2 and 0 is 2. 9 and 4 is 13. 13, we carry the 1. 1, 2, 3, 4, 5, 6. So 2,632. Alrighty. And just because numbers do eventually get larger, one more set of example, to which we have 573 times 205. Now we're going to do from left to right because I'm more comfortable with that, and then we'll also do right to left because some other people might be more comfortable with that. So I'm going to go with the 2, which is in the hundredths. 2 and 5, which is also in the hundredths, is a 10. 2 and 7 is 14. 2 and 3 is 6. There's nothing here in the 0 spot. So if it's anything to do with this 0, know that 0 times any number is 0. This is particularly due to there's a particular word for it, but hold on. I'm sorry, I do not have this exactly on hand. Very well then. So I cannot locate the proper name for this. However, this is a fundamental, basic item with multiplication. So if I were to multiply the 0, which is in the tens place, by the 5, 0 and 5 is 0. Excuse me, it's in the hundred spot, so it's 0. 0 times the 7, which is in the tens spot, is also 0. And 0 times the 3 is 0. And 0 plus 0 plus 0 is all 0. So we didn't really need to multiply by that 0. It'd have been easier to just have skipped it. But we did this because examples are for illustrative purposes. So there's nothing to use in the 0. So then we go to the 5. 5 times 5 is 25. 5 times 7 is 35. And 5 times 3 is 15. And now I've used up all of that. And now we have a simple sum. I said a simple sum. It's a long sum, but it's simple. So then all these zeros and a 5. All these zeros and a 5 plus a 1 is a 6. That's 6. Plus 5 is 11. Plus 3 is 14. We carry that 1. 1 plus 4 is 5. 5 plus 2 is 7. And 1. And 1. Don't forget your commas for easy reading. Alright, and that was from left to right. So then we have 573, 205, from right to left, with carrying, because right to left can be carried. So we start with 5 in the ones place, 3 in the ones place. 5 and 3 is 15, carried to 1. 5 and 7 is 35, plus 1 is 36. 5 times 5 is 25, plus 3 is 28. Like that out, and 0 times any and all of this is 0. So we don't necessarily have to write that, as it will just create a row of zeros. So then we have in the hundreds place, 2 times 3 is 6. 2 times 7 is 14, carry the 1. 2 times 5 is 10, and 11. 5 and 0 is 5. 6 and 0 is 6. 8 and 4 is 14, carry the 1. 1, 2, 3, plus 4 is 7. 1 and 1. Alrighty then. I think that covers the basics of multiplication as far as we've gone over. And because we start with multiplication, the making bigger of something, we will go with now the division. Simple division, where division is essentially the serial subtraction of a number from another number. So if you're given a number, say 48 divided by 8, that is subtracting from 48, 8, until it becomes 0. So 48 minus 8 is 40. 40 minus 8 is 32. 32 minus 8 is 24. Minus 8 is 0. So that happened once, twice, 3, 4, 5, 6 times. Therefore, 48 divided by 8 equals 6. Now I've written it with the division sign. However, this can also be written as 48 divided by 8, or 48 divided by 8, which this particular notation is very good to keep in mind, especially when getting into fractions at some juncture. It will be coming up. This is a very nice and easy notation. So a quick note back on the denominate numbers. So let's say you have $15 for 3, let's say buttons. Because $15 for 3 buttons. These are very special, nice buttons. So that is like, what is 1 button worth? So that means for $15 worth of buttons, which is 3, what times 3 is 15? So 15 divided by 3 equals what? Which also means 15 equals 3 times what is 15. So 15 minus 3, which would be 1, be once, twice, third time, comes out to 1, 2, 3, 4, 5 times. So 1 button is $5. Or written in a different way is $5 per button. Alrighty. Alright, going into some more division as far as an example. There may be times, especially all the time, more often than not, we'll get some number that is divided by another number that doesn't subtract neatly. That is to say, 49. Excuse me. In this example, we have 49 divided by 8. 49 minus 8. 41 minus 8. 33 minus 8. 5 minus 8. 17 minus 8 is 9. 9 minus 8 is 1. Now 1 is smaller than 8, so we can't subtract 8 from this unless we get negative numbers, something we'll deal with in a later episode. But for now, we have a 1 left over, or it is the remainder. So if you have a question that has 49 divided by 8, and you know that 8 can fit into 49 6 times, 1, 2, 3, 4, 5, 6 times, minus 6 times 8, which is 48. 49 minus 8 is 1, so you would have a remainder of 1. Alright, I kind of have a personal favorite topic with division, specifically long division. Get a little out there so you can see everything. So long division, very simply put, it's a little longer than non-long division. So if we have an example, let's say 176 divided by 8. Long division is usually set up in 176 divided by 8, so that we can keep working downward as we go. So instead of using a series of subtraction, I'll go ahead and use the basic understanding that 8 times 2 is 16, is the biggest number that fits into 17. So if you were to subtract 8 from 17 twice, you would get 1 as a remainder. But as we have this 6, we can now bring it down. And 8 can fit into 16 a neat 2 times. So 16 minus 16 is 0. There are no remainders. So therefore, 176 divided by 8 equals 22. Easy peasy. And then, because we're all about checking answers, and something that I should have done previously to show you, is that to check your answer, that 176 divided by 8 is 22, you get to multiply it. So you get to multiply 22 by 8. Left to right is, and 2 times 8 is 16, and 16. And 22. So 2 times 8 is 16. Carry the 1. 8 times 2 is 16. Plus 1 is 17. 176. So yes, that is correct. All right. A fun little aside is, what if you get the example of 8 or some number divided by 0? What does this equal? Well, this implies, oh my goodness, this implies that 8 equals 0 times that something. We have just gone over that anything times 0 equals 0. Therefore, because this is true, this cannot be true. Whatever this is does not exist. It's not a thing. And because it's not a thing, we can't define whatever it is. So the answer to this is simply undefined. Or in shorthand, undefined. Because dividing by a single digit number is in fact too easy, we have another example therein of a 2-digit number. Let us see. So we have an example of 293 divided by 38. Now this is kind of where math gets a little touchy-feely. So you just look at the first bit to see if 38 can fit in anywhere. If 38 cannot fit into that 29, you can put a 0 here just to let you know that it can't fit into any of that spot. But then you'll have to see 293 if it fits into anything. Something you can do, especially since for 2-digit numbers, it's a little more complicated. Something to make it simple. Since 38 and 293 seem complicated, to make it seem a little easier, we can round to give a nice, apparently easier math problem to deal with. We can round this up to 40, and we can round to 90 down. And because they both have zeros in the one spot, you can simply look at it being 29 divided by 4. And 4 can fit into 29 7 times. So because 4 can fit into 29 7 times, that would mean 38 can fit into 293 7 times. So you may have to do this on the side. But then you get 7 times 38. So 3 and 7, 8 and 7, so that's 266. So you're subtracting 266 from 293. 2 from 2 is 0. 9 and 6 is 3. Excuse me, borrow 8 is 3. That'd be 2. 13 minus 6 is 7. So then you get, because 38 can't fit into 27, you get 7, remainder 27. So in order to check a problem that has a remainder, that would be showing that 293 equals 38 times 7 plus 27, whatever that remainder is. So we just shown that 38 plus 7 is 266 plus 27, 293. So 6 and 7 is 13, carry the 1. 1 plus 6 is 7. 8, 9, 293. And one more lovely example of just why division can get so unruly. The example of 32 dividing 9871. And again, kind of getting a feel for it, we can round. We can round the 32 down, and we can round the 9871 also down. So 30 can fit into 987, but they both end in zeros, so we end up having 3 dividing 987. Oh no. I see where this can go very wrong. Hold on. Bear with me. So 3 into 9. I'm actually curious as to why this is going so wrong. 3 into 9. 3 times 3 is 9. So 0. Bring down the 8. 3 can fit into 8 twice. Minus 6, which is 2. Bring down the 27. Or the 7 for 27. And 9 times 3 is 27. 0. So there is no remainder. So answer would seem to be 329. So 329 should be your answer. We check the answer by 329 times 32. And we'll go from right to left this time. 2 times 9 is 18. Carry the 1. 2 and 2 is 4. Plus 5. Plus 1 is 5. 2 and 3 times 3 is 6. And in the tens place, we have 3 times 9 is 27. Carry the 2. 3 and 2 is 6, 7, 8. And 3 times 3 is 9. You see how it all fell apart? I believe it had to do with turning this into this. This was an incorrect step. I apologize. The question should have been, we shouldn't have taken the 0 off here because this 0 and this 0. One moment, please. Yes, I am referring to a calculator just to check my answer. If you have the availability to do so, I would recommend it. Okay. So if we were to keep the rounding, do not drop the zeros. What you will do, 9870, is to see how many 30s can fit into 98. We know that it takes 3 times 3 to get a 9, so it would be 3 times 30 to get a 90, because being in the 10th place, there's a 0 behind it. So you have an 8, we drop the 7, and this is no longer a 90, so we're just going to, we know that it's going to at least be less than 3. So 2 times 30 is 60. So you know how I said in the first video that these early videos are going to have a lot more mistakes than corrections? This is one of those second mistakes, so hold on. If you feel like you have messed up in any part, don't be afraid to scrap it and start over. So I'm going to use another side of this paper, hold on, and we're going to just start completely over, because that is what I feel more comfortable with doing at this point. In this case, we would not have to round. If we were just to feel for it, it would take 3 30s, kind of like in the rounding, to fit into 98. So 3 times 3 is 9. 3 times 2 is 6. So you would go ahead and subtract this one. So then 98 minus 6 would just be 2. We drop the 7. We can't fit a 32 in the 37. This is where it all had broken down before. So then we drop the 1. So we can fit 32 in that 27. So if we were to guess, 27 and the 3, you would think 9, but then 9 times 2 is 18, which is bigger than 1. So we will work with 8. So 8 times 32 is 24, 240, and then 8 times 2 is 16, so that'd be 256. So 2 minus 2 is 0, 7 minus 5 is 2, 1 minus 6, that is 11 minus 6 is 5, so that would give a remainder of 15. So to check your answer, as we've had mistakes up to this point, and that would warrant it being checked, so that should be 32 times 308 plus 15. And we have shown that 32 times 308, well, we have not, have we? So 308 times 32, 2 times 8 is 16, carry the 1, 2 times 0 is 0, bring down the 1, 2 times 3 is 6. 3 is in the tens place, so we have a 0. 3 times 8 is 24, carry the 2, 3 times 0 is 0, bring down that 2, and 3 times 3 is 9. So we have 6 and 0 is 6, 1 and 4 is 5, 6 and 2 is 8, and 9 by itself is 9, plus that 15. So I'm bringing it over here for ease. 6 and 5 is 1, 1 plus 5 is 6, plus 1 is 7, 8 plus 0 is 8, 9 plus 0 is 9, and that is checked. So that means our 308 remainder 15 is correct. Thank you for your patience. We got there. Alright. Division does seem a lot more straightforward if you have understood multiplication first. And understanding multiplication is very important as it is the basis of a lot of things done in math later on, such as exponential notation and order of operations. So exponential notation looks something like 3 to the 4th power. And kind of like 3 times 3 means we are adding 3 times. 3 to the 4th power would mean that we are multiplying 3 4 times. So 3 times 3 is 9. 3 times 3 is 9. 9 times 9 is 81. So to write something, let's say 2 times 2 times 2 times 2 times 2 times 2 times 2, that's 1, 2, 3, 4, 5, 6, 7 2's, 2 to the 7th power. Yep, 2 to the 7th power. And if you want to, 2 times 2 is 4. 2 times 2 is 4. 2 times 2 is 4. We don't have anything with a 2. 4 and 4 is 16. 4 and 2 is 8. And 16 times 8. Carry the 4. 8 and 1 is 8. So 128. So, as one more set of examples, is that we have 5 to the 3rd and 8 squared. 5 to the 3rd is 5 times 5 times 5. 5 times 5 is 25 times 5. 25 times 5. 5 and 5 is 25. 5 times 2 is 10. Bring down that 2. Be 125. And 8 squared is 8 times 8. 8 times 8 is 64. And understanding, so we have like 3 to the 4th, we have 5 to the 3rds, and 8 squared, or 8 to the 2. So if we had some number, let's say 9, raised to the 1 power, that is 9 times what? That is just 9. There's no other thing to multiply with. It didn't say. There was only one 9 to multiply, and there's nothing to multiply by that 9. So the answer would just be 9. And it would be that way for any number and so forth. Okay. We have come to understand the importance of the order of operations. So you may have seen and I may have written it wrong on my title card. You'll have to let me know. As far as order of operations. We have parentheses, exponents, multiplication, division, addition, and subtraction. So, most people that I know understand this to be, please excuse my dear Aunt Sally, whatever mnemonic device you have to remember this particular order, that will work for you. If it's inappropriate, keep it to yourself, but if it works, it works. So, a lovely example herein would be 4 times 2 to the third. Now, because there are no parentheses, we don't have to do any of those first, but there is an exponent, so we do this part first. So 2 to the 3 is 2 times 2 times 2. So 2 times 2 is 4, times 2 is 8. So then we bring down that 4 times while it waits patiently for this to be done. 4 times 2 is 8. Now we can do that initial multiplication, which 4 times 8 is 32. All right. Okay. Oh man. See my hands. Come back. Okay. All right. So we have several lovely examples of order of operations. As order of operations is pretty much the basis of any other types of math going forward. So let us see example. I'm going to call this example 25 as it pertains to number 25 in the textbook I am using. It's very important. We have 7 minus 4, that to the power of 4 minus 30. So we have parentheses? Yes, we do. So we do what's in parentheses first. 7 minus 4 is 3. And we can keep that in the parentheses, but we don't have to, as everything in the parentheses has been calculated. We bring down the 4, who's weighted, and the subtract 30, which is weighted. Parentheses, exponents, yes, we do. So 3 to the 4th is 3 times 3 times 3 times 3. 3 and 3 is 9. 3 and 3 is 9. 9 and 9 is 81. We bring down that minus 30, as it's also been patient. And 81 minus 30 is 51. All right, so we have example number 45. In parentheses, 3 to the third power plus 3 divided by 10. So we have parentheses, yes, but inside the parentheses we have more things to address. So inside the parentheses, do we have any parentheses inside? No. but we have an exponent on the inside. So 3 to the third is 3 times 3 times 3. 3 times 3 is 9 times 3 is 27. Bring down that 3 in parentheses, divided by 10. And now we can do everything in the parentheses because we have calculated this down. So in parentheses, 27 plus 3 is 30. Everything inside the parentheses is done, so we may drop them. So 3 divided by 10. Parentheses, exponents, multiplication, no. Division, yes. Multiplication and division can be done at the same time, but I'll give an example as to why the how and when of there is very particular. So 30 divided by 10 is 3. Alrighty. So my personal favorite example of why multiplication comes before division in some cases and in other cases. So we have 4 times 4 divided by 4. Which either way you do this. So let's say we address this part first. 4 times 4 is 16. So 16 then divided by 4 is 4. But now let's say we started this part first. So we have 4 times 4 divided by 4 is 1. 4 times 1 is 4. In this particular case, it all worked out. But if we were to have 4 times 2 divided by 4, 4 times 2, if we were to do from left to right, 4 times 2 is 8 divided by 4. 8 divided by 4 is 2. This is the other way. We have 4 times 2 divided by 4. 2 divided by 4 is 1/2. And 4 times 1/2 is the same as, bear with me, 4 times, no, we just said divided by, 2. So 4 divided by 2 is 2. Because we know this to be the notation of 1 divided by 2. So if you were to rewrite 4 times 1 divided by 2, as it is, nope, never mind. I was going off on a unrelated tangent. That's not how that would have been addition or subtraction. My mistake. I was about to go off the rails. But nope. 4 times 1/2 is 2. So again, this works out. So you can do multiplication and division in any order. Alrighty, let us see. I think the only thing left to have in this abridged initial review is geometric applications. So a lot of that is taking the multiplication, addition, subtraction, exponents to address basic geometric applications. So if we have something arbitrary, 1, 2, 3, 4, 5. This is not drawn to scale, bear with me. And we say this is 30 feet, 45 feet, 25 feet, 18 feet, 20 feet. The perimeter is the sum of the sides of a shape. So it's the fence. So if we're looking at 30 feet, 45, 25, 18, and 20 feet. We're trying to figure out how much fencing we need to encompass the space, or some length of feet. That is the sum. So we have the 30 plus the 45 plus the 25 and the 18 and the 20. So 5 and 5 is 10 plus 8 is 18. We carry that 1. 1 and 3 is 4. 4 and 4 is 8. 8 and 2 is 10. 11, 12, 13. 138 feet as a perimeter. And because we have added this, it still remains feet as it is a distance. All right. Another example, another quick example of this would be, say this is 28 inches. So if ever you see the notation of 28 inches, it's like this. But the shorthand of feet is 25 feet. So if someone is 5 foot 6 inches, that's what it'll look like, just for notation purposes. Because ditto marks or quotations is much easier to write than the whole word inches or feet. Just thought that would be nice to know. So 28, 15 inches, 50 inches, and 24 inches. Notice how this is drawn smaller than that. This is not drawn to scale. So again, the perimeter here in this example would be 28 plus 24 plus 15 plus 50. 8 plus 4 is 12. 12 plus 5 is 17. 17 carry the 1. 1, 2, 3, 4, 5, 6. 6 plus 5 is 11. So that'd be 117 inches. Now we have the perimeter. Let us find the perimeter of a regular rectangle. So what that means is, in this example, if I draw it nice and neat, if we are given that this side is 8 inches and this side is 5 inches, because this is a regular rectangle, that means this side and that side is the same, and this side and this side is the same. So to find the perimeter, we need this, that, and the other sides to sum to get the perimeter. So we have 8 plus 5, and this side is also 8, and this side is also 5. So 8 and 5, and 8 and 5. So 8 and 5 is 13, and since this is 13, 8 and 5 is also be 13. 13 and 13, which would be 26. Now another way you could do this is, because you have the two sides given to you, 8 plus 5, which equals 13, you have these two sides again, so you multiply it by 2, which is 26 inches. So another quick example of that is 12 inches by 7 inches. So you could do it either way. You get 12 plus 7 plus 12 plus 7. Or you can get 12 plus 7 multiplied by 2. So 12 plus 7 is 19. 19 plus 12 is 20, 31. 31 plus 7 is 40. Excuse me, I'm sorry. Nope. I didn't quite number there. So 19 plus 12 is 20, 31. 31 plus 7 is 38. 38 inches, which is 19 times 2. If we were to do it this way, 19 times 2, which would be 20, plus 18, which would also be 38. Yep, it'll be 38. All right, and if I can squeeze in the last 6 minutes here, the area of a regular square and or rectangle, I think I will be content. Or we may have to go over area next time. There seems to be a lot of funky attributes as to different areas of different items. Quick overview. As a perimeter is the sum of all sides. Which, if the unit, whatever unit, let's say some number of units, the sum of all sides that have sides unit 6, that sum will also be labeled in units. So if it was inches, it would be labeled in inches. If it was labeled in feet, it would be labeled in feet. Where the numbers we sum would be labeled, the answers would be labeled the same as what we were adding. As there's a lot more notation for area going forward, I will pause that for now and readdress it in the next video. Any questions, comments, concerns? Somebody will comment probably months after this, and I will try to get back to them eventually, but we shall see. Beyond that, that's where we will end this video this time, and I will see y'all next Tuesday, the 4th of July. I don't anticipate anyone on the 4th of July, but I will still be here. Bye!